and I'm with my partner here, Annabelle. Our project is deep learning to distinguish H2 regions from galaxies. We're at the University of Texas. I'm a physics major and she's a computer science major. So outline of the project, overview of the presentation. So what are H2 regions and why are they important? We're going to talk about pipeline methodology, results, and future directions for this research. So the purpose of the project is to create a pipeline and a repository of H2 regions. There is a problem right now distinguishing between these H2 regions, which I'll explain in a minute, versus galaxies, nearby galaxies, which is quite nuanced to distinguish between the two. There are statistical methods, however, it's a bit more involved. So what are H2 regions? H2 regions are pockets of ionized hydrogen gas that surround an O or B type star. There are 4 different classes of H2 regions, with the most compact being called hypercompact regions, and the least compact being called classical regions. They differ wildly in terms of density, with hypercompact being on the order of 10 to the 6th atomic mass units per cubic centimeter, and classical being around 10 atomic mass units per cubic centimeter, which is a factor of 1,000,000 difference in density. The reason they're considered to be the same astronomical objects is they have a lot of the same underlying physics and phenomena underlying them. Hypercompact regions are unstable. They normally last only a couple 100,000 years, while classical ones are relatively stable. They also produce the forbidden line spectra. So what are forbidden lines? With hydrogen, you get, with just regular hydrogen at a reasonable pressure, you get a distinct spectral graph. So we have discrete emission lines. However, with rarefied hydrogen, you get a separate emission line called forbidden lines that we've been using in this project to discern between the two. So why H2 regions? There are a number of applications for this research. One is extinction mitigation. The idea is you have these pockets of hydrogen gas that are kind of obstructing things in the background. And so if you know where the H2 regions are, you could expect a certain amount of distortion of the objects behind, which might be advantageous for further classification. Another application of this research is star formation research. So these H2 regions are fuel for stars, fuel for further stars. And so we could create a repository that would be advantageous for research in that field. So background and data. For our training data set, we used a couple different pre-assembled repositories, 4,900 labeled H2 regions and about a similar number of galaxies. A lot of the H2 regions were classified using radio recombination lines, and others with forbidden line spectra. So an overview of the pipeline. What we do with the actual pipeline, a general overview of it, is we outline a stamp in the sky, which is around 7,200 arc seconds in length. So it's a square with sides 7,200 by 7,200. We pull the square images from the IRSA database. We feed these images through a gradient filter, which I'll talk about in a minute. The gradient filter is a quick way of determining whether or not an H2 region, or sorry, an image is a good candidate for an H2 region or a galaxy, and throws it out if it's noise or just a random image, and keeps the interesting ones for further computation. The next step would be to feed it through the convolutional neural net, which is a bit more nuanced than the gradient filter, and determines with a higher accuracy whether or not we have an H2 region on our hands. If it determines that this image contains at least one H2 region, we then break down the image into 9 subdivisions, so 9 sub-images, and we feed it back into the gradient filter. And this ensures that we get all of the H2 regions within an image, rather than having 6 or 4 or 3 H2 regions within the image and classifying as the whole thing as an H2 region. So the first major part of the pipeline, which I just talked about, is the gradient filter. And the gradient filter is just a fast way of determining candidates for H2 regions. Its only objective is to reduce the computational load. And the filter works by creating a gradient map. So we have this image, that's the the brightness per pixel from the UV-wise telescope that we're getting our data from. And we calculate the gradients by looking at a central region of a number of pixels. Then we look at the adjacent regions and we see if there's a bias in any sort of direction. We then normalize that and count them by number. So this eliminates point sources with high magnitudes dominating our gradient filter. And it allows gradients over a larger distance to be more prevalent. So this right here, the image I'm showing on the screen, would be classified as a candidate for an H2 region. And the features we're looking for is these sort of floaters, or maybe snake trails they look like. This is evidence of some massive structure. So that's the main thing the gradient filter looks for. If we see evidence that there might be a structure above a certain threshold, then we recommend it for further computation. This is very convenient because it just gets rid of 94% of the initial data with very little computation. Here's a diagram explaining what I just said. And I'll let Annabelle take over.
Onto the classification pipeline, the last component really, the convolutional neural net. So Alan did explain earlier about H2 regions and how they're represented astronomically, but the neural net is really just concerned with how they are represented graphically. And so to give a little bit of background on the data set we're working with, as we mentioned earlier, we're extracting at a particular passband, the W3 passband, which captures wavelengths from 10 micrometers to about 23 micrometers. And so that's adequately capturing the forbidden line spectrum, which is good. That's what we're looking for. And it also has enough resolution for us to have to take a look at those detailed structures that Alan mentioned, the gaseous structures that would help us distinguish between H2 regions and galaxies. And so because of this, though, we're only extracting at the single passband. That's basically just a single color channel. So our data set is, reduced by that magnitude, since a lot of these classification pipelines are accustomed to multiple, maybe 3 or 4 color channels. And so because of this, we could get away with removing some of the dense neurons. So inside these fully connected layers, which is the second component of a convolutional neural net, we could remove about 10% of those neurons. And this helps combat overfitting, as well as any computational, as well as some excess computational overhead. And inside the feature extraction portion of the neural net, we also reduce the kernel window from a 5x5 window to a 3x3 window. And again, both of these reductions of parameters are to help with efficiency. Since again, a lot of this is handled either through the gradient filter or there because our data set is not overly complex to begin with. So, right, so as I mentioned earlier, the CNNet architecture, I believe it was mentioned here, is modified from AlexNet. We did attempt to work with other designs, other architectures such as VGGNet and SegUNet. We'll talk a bit more about those later in the application part of this. And so in terms of preprocessing for our data, we worked with grayscale images, like I mentioned. We had affine resizes to make sure that they fit for our pipeline, which just intook a 256 by 256 pixel image. And we also did normalization as is typical. Instead of batch normalization, though, I will say we did use the local normalization, which is typical for AlexNet, simply because the batch normalization led to inconsistencies in our performance in terms of accuracy. Right. And so some interesting findings we had because of this, though, is that, well, I guess I can take a step back and talk about arc seconds. So our approximation for sizes for these images, if you think about arc seconds as like approximation of our radii of the image. So 3600 arc seconds makes up 1 degree. If you think of the sky as sort of a dome, that's about 1 degree of space, like a 1 degree large image, I guess, extracted from by the telescope, by the WISE telescope. And so what we saw here is that there's a linear distribution of can we classify if an image contains an H2 region, and that tends to go up with the size of the image. Our initial theory was that we had really low accuracy at really small images because of the internal structure of the H2 region. So we believe that because H2 regions contain stars inside of them, which are ionizing the hydrogen gas and thus creating a structure, if we zoomed in very far and we saw that there were only stars within an image, it could easily be misclassified as a false negative to be either a galaxy or just noise. Eventually, though, we adapted our gradient filter to handle this case. And that's also how we know that our gradient filter, the recursive grid division portion of the gradient filter, is, it is guaranteed to terminate because we'll reach a point where we have zoomed in so far that it's we've reached a point where we zoomed in so far that we see either just bright points, which are either too far to classify or not indicative of any structure, and the gradient filter will eventually discard all images. And from there, the process will terminate. And so this also means that because higher images, or larger images rather, are more easily classifiable, this sort of segmented data augmentation as vital to our pipeline. And so that's another portion on top of the convolutional neural net that we have. Sorry, yeah, that's probably fine. So on top of the convolutional neural net we have, we also did data augmentation. So with our 4900 original H2 region images, we took various snapshots at further distances or closer distances, depending on the size of the region. And so that expanded our data set by about 4 times to a total of 39,000 images. We had originally 4,900 H2 region images and 4,900 galaxy images. All right, and so from here, in terms of how we've accomplished our research goal, we set out to make this pipeline, and we found one that approximates, or with appreciable accuracy at about 85% for very large images. Although we initially believed that it was because of very zoomed in images being misclassified as false negatives, we now believe that it's because that we have higher accuracy with larger images because of inclusion, where if you just have a larger image with more H2 regions, you're more likely to see more H2, you're more likely to accurately classify it as having an H2 region. And then with the recursive grid division, we can get a lower bound on these specific coordinates of these H2 regions. I will also say specifically for working with images of astronomical data, or astronomical images rather, data augmentation is the most effective technique we've seen for increasing your accuracy. It's a low overhead technique, and also there's the closer features that are specific to your H2 region are difficult to distinguish with filters unless you have this data augmentation technique, which allows you to take a step back and force recognition of H2 images regardless of your zoom level. Here's some notable features that were extracted at the first layer of output. So again, the AlexNet pipeline has about 4 layers of feature extraction. This is from the first layer. As you can see, larger images have a much better, much easier time of recognizing these gaseous features. Sorry, I'll try and speed through these. And in summary, we found an effective way to preprocess astronomical images for classification using a convolutional neural net. From here, we'd like to use more widespread classification for different types of objects, and also start building a repository of H2 regions. In further studies, we'd like to incorporate instance segmentation, which we're approximating with our grid division, but would be more effective to analyze compound images. And we'd also like to use this preprocessing in our pipeline for general use in astronomy. As I mentioned earlier, we did experiment with different CNN architectures, and as long as the architecture itself is customized for your dataset, as we did for AlexNet in our more sparse and less complex dataset, we believe that this is a reasonably effective technique in preprocessing images for classification. We acknowledge the assistance of where we got our data from. Apologies. So the Galaxy's second data release, and O.D. Anderson et al., who provided the WISE coordinates for our H2 regions. And then additionally, we acknowledge the assistance of members of our Geometry of Space research group and our advisors, Dr. Carl Gebhardt and Dr. Shmuel Mitra. Thank you for listening. We're open to questions.
Okay, thank you guys so much. So the judge, do you have any questions for the presenter?
Yeah, could you speak a little bit more about your data set that you used? So you mentioned, I think at the end, you got it from, was it an existing research project? Could you explain how you found your data set?
Sure. We have a couple different repositories of H2 regions identified through several different methodologies. namely radio recombination as well as forbidden lines. And so we just sort of concatenated all of these repositories together. They were all labeled. We have the sky coordinates of them. We take these coordinates and we get it from the same data set. So there's this something called the WISE telescope, which we're getting all of our data from. Does that answer your question?
Right. So these were existing research projects that published their data sets like open source.
That's correct. I should specify we're only getting the coordinates to these H2 regions and galaxies. We put these into something called an IPAC file, and we see a spatially coincident image from the WISE data set.
I see. Okay. And did you all need to perform any sort of data cleaning or removing any data points from your data set?
I suppose so. We use something called an affine transformation. So not all the images are going to be 256 by 256. So we scale the image up or down depending on what the actual dimensions of it are.
Okay, great. And in one of your slides, you had a visual about the performance of your model versus existing models. Yeah, could you just go back to that one really quickly? Yeah, that one.
Sure.
So
comparison of architectures here. But
right. So where did you get the performance data for those other two models?
what we did was just take the AlexNet, SIGINET, and VGG6 16. We have the architecture from that. We retrain the models and then we verify. So this is the comparative accuracy of those different models.
Sorry to help them, but specific to these models, we found that AlexNet performed better since the added depth for SIGINET and VGC16 often led to overfitting. We also found it difficult to debug because of the batch normalization versus local normalization. And so again, these are models that we trained from scratch and then adapted, hooked on to the end of our pipeline, and just measured the performance from there.
I think that's all for questions. Thank you.
Thank you.
Does anyone else have any other questions for these presenters? You can raise your hand or type it in the chat if you'd like. Okay. All right, we'll move on. And thank you guys so much for presenting. So our next presentation is going to be from Daniel from University of Houston. Daniel, if you can go ahead and share your screen and get all ready. So judges.
Can you hear me?
Yes, we can hear you.
Okay, and can you see the screen? I should be sharing it right now.
Yes, looks good. Judges, are you ready to start the next presentation? Okay. So can you introduce yourself and by your school and your study?
Yes. I actually, so you can see the presentation well. I have like a weird thing going on right now. So you see like the entire presentation or like
Yes.
normal, or you see some extra stuff?
No, there's other things.
Yes, I'm sharing the wrong screen.
All good.
Okay.
No worries.
Okay, so what about now?
Yes, all good now.
Okay,
Okay.
great.
Ready? Okay, cool.
Yes. So
just to make sure,
so-
can I record this presentation?
yes, you can
Okay,
record it.
cool.
So I'm Daniel Palacios. I attended the University of Houston, and I have been an intern at NASA since last year. And I'm going to be presenting my project there, which is about natural language processing and machine learning to analyze space hardware failure reports. So this is just a list of the general things we're gonna talk about today. So since we don't have that much time, let's just start. So a little bit of my background. I'm a physics and math major at the University of Houston, and I'm gonna graduate this May. So I don't come from like a engineering or machine learning background. So I self-taught myself Python and other languages. And starting on August, I'm going to start at Baylor College of Medicine in a PhD program. So I'm very happy for that. Some other of my experiences. So during my freshman year, I worked at Rice University in gene regulatory networks. I also took some other projects in physics in quark-gluon plasma viscosity, which is the state of matter that we had during the Big Bang, which is very, very interesting. It was very fun. I also did some asymmetric superconductivity research at the University of Houston. And so I have been an intern for more than a year now at NASA. So we're gonna be talking about that right now. So a little bit of background of my project. So I work in Johnson Space Center. So we went, NASA went from paper to digital databases. And one of these databases is called the discrepancy reports, which form around like 54,000 document sets. And here, engineering or technicians report what went wrong with the hardware that was sent to space or software also. And these documents consist on some unstructured text where people describe what was going on, some structured tests that they have some classification and like final dispositions and numeric data like dates, of course. So of course, going and reading them one by one is unpractical. So this is where the big data tools come from, handy. So we want to analyze this text and identify trends, correlations, and generally just extracting knowledge, text mining, right? And identifying root causes. So of course, I won't have time to talk about all the stuff I have been doing. I just want to highlight that it wasn't just, oh, I found this model and I use this model and oh, I'm done, right? I would say that we know that in machine learning and big data tools, sometimes you need to dig up and find the ideal model that works best for your data set. So it was kind of like an exploratory adventure. So I tried a lot of different models here. So it also increased in complexity horizontally, right? So I started with just running some pre-processing techniques. And then I went there and did some topic modeling. And then I combined this topic modeling with text classification to kind of give me more sense of validation. And then after analyzing the general results, I move on and use other techniques like feature extraction clustering. And so there was some substructures in these classifications that I had. So I decided to create a taxonomy. And so taxonomy just refers to, it's very like biology, right? So you have a way that you classify like species, right? And you have families. So I did the same thing. So I'm gonna be showing it later, but you had a form of classification that already exists, and then I expanded to process labels and sub-process labels. And I also use some commercial tools like AWS and IBM Watson Explorer, and actually I think like the capabilities I was developing outperform these commercial tools in our specific use case. And then I use Power BI to analyze trendings and correlations and create these dashboards and identify high trending, high relevance phrases and concepts in this data set to bring attention to monitoring capabilities of the engineering management at NASA. and support our future lunar missions. I also did some work with interactive knowledge graphs. And yeah, let's move on. So I'm just gonna talk about like the general models that were kind of the most useful, or the keystones there. So a little bit of topic modeling. So topic modeling here is just a model that reads through all your text and generates a list of topics, and then it assigns a probability of these topics in your document. So let's say it says is 75% topic 1 and 25% topic 2, right? So it is a way, it's very useful because we don't have a classification in these documents, right? And doing this list of topics, they can be engineering processes themselves, common phrases that it found in the documents, and general like concepts there that are very important, because then we can go and analyze them, and your typical histograms and ways of looking at these keys and weighting them across other variables in the data set. So a little bit of the taxonomy. So I talk about that I run some feature extraction clustering, and then I saw that there was some substructure. So I decided to run this LDA BERT model again. I don't talk that much about BERT, but BERT uses transformers, and it's a model that Google, I believe, developed. And here I'm using its text classification capabilities. So I use that, and I optimize the hyperparameters there and find the best model that gives me the best accuracies there. And now I have a taxonomy that I'm gonna show in the next slides. But yeah, so let's move forward. So I also did some cause-effect relationships. So I tried several models for association rule mining. And this one was the one that gave me kind of the most useful results. So Indra was originally developed for biology application, and ADOS was this extension that applied to general cases. So I use this model, and this model is very handy. It extracts not just causes and effects, but events, annotations, parameters there. But in my use case, I was just concerned about the causes and effects, because I wanted to identify common causes of these engineering processes problems, right? And I also use some Markov chains to analyze my data. So what is a Markov chain? It's a very simple algorithm. So it just goes, well, you map a dictionary, and in this dictionary, you have the word and the next word that follows. So you have a distribution of words that it follows that document. And then you weight those distributions. So you ask, okay, what is the word that is more likely to appear after this first word, right? And in that way, you can construct these interactive nodes, diagrams, and you can start forming sentences that can give you a better idea, instead of going and reading all the subgroup of text, right? So here is how the taxonomy looks like. So something that came very handy is like, so there is the first way of classification. It was an existing way of classification that NASA used. And some of them were unlabeled. So they didn't have a specific code for them, but my model doesn't need to use those codes. It just goes and reads the text, right? And it assigns a classification based on the text. So I could go there and label documents that were previously unlabeled. And the other handy thing is like it extracts me some phrases and general ideas that we are going to be using to group this text, and then you can say, okay, I mean, this group of texts have this trending, right? And this group of text has these correlations, and this sub-process relates to this sub-process. So it becomes very, very nice. And you can also do some trending analysis. You just plot the time series and use some machine learning to kind of do predictions of the behavior of these sub-labels or sub-branches of the taxonomy. Another thing is, so whenever you cluster these causes and effects, right? So the blue nodes correspond to the effects and the green nodes correspond to the causes. So whenever you plot them in these graphs, interactive knowledge graphs, you get this clustering that you can use to look at the source nodes, and these causes that generate multiple effects, those would be your root causes, right? And yeah, the correlation analysis that I talked about already. Some major accomplishments. So I'm gonna publish my work at the Stripes at the NASA publishing thingy, and I'm gonna be also, we are looking for a publication in Frontiers, but we'll see how that goes. I posted kind of my code, these models to the NASA AI ML group. There is a community group within NASA where we discuss machine learning and AI technologies, and I share this code for them. So if you have a VPN at NASA, you could access these codes and use them in your project. So it was a very nice experience, because I got to impact not just my project, but also try to help other people in their projects that they would like to use similar technologies. So as I was saying before, I was able to identify high trending and high relevance of these phrases and bring them to attention to the engineering management, because we really want to learn from the past, right? And from past lunar missions, from all other types of missions. So in the future lunar missions that we're gonna have with Artemis, we don't commit the same mistakes, right? And I also presented a poster, and actually, like, is it same thing I'm presenting right here? Oh, looks like my time is up, but I mean, just general acknowledgements. I work with a lot of people across NASA from a lot of different centers, and yes, and I think that concludes my presentation. Thank you.
Thank you so much. The judge, do you have any questions for the presenter?
Yeah, would you mind going back to your slide about the clustering of the data? So
Yes.
you had a visual about
This one right here.
I think it was before that.
So let's see.
Oh, yeah, the yellow and purple. Yeah.
Oh, this one. Okay.
Okay, so could you explain a bit more about the clustering algorithms you used?
I believe here I use the principal component analysis, I think was it called. So yeah, so how it works is like you have features in your text. So I use, I mean, it's high dimensional, right? You have like a lot of dimensions, so you cannot cluster these things in like your conventional way. So the way I did it was, I'm pretty sure I use another one that I don't recall the name. I might have it right here. No, I use a PCA and another algorithm I tried, but I think in this specific plot I use PCA. So it just maps these high dimensional systems. You just collapse them in a 2-dimensional space, and then you can run a clustering. I cannot recall what I think it was a very simple one from sklearn algorithm that I used to create these two subgroups. But I would look through my notes because I did this this was one of the things I did like a year ago, so it's not very recent. So I cannot recall the specific model that I used, but I can go through my notes and let you know. Send you an email.
Did you consider using any shape-based clustering algorithms? For example, just looking at your visual, you have a yellow round section and a purple round section. Did you ever use anything like Gaussian mixture models or any other shaped-based classifiers?
No. I think I just stick to the very basic one. So the sklearn, I use sklearn, and they had a documentation where you had a lot of different ones. I think I just stick with one of the first ones. No, I didn't go over there. This thing, I just use it to justify that there was some substructure in my classification, right?
Okay.
So, and then I run the model again, and you can say I computed some researches, and then the one that had the optimal number of sublabels, I use those number of sublabels to create my taxonomy. So I didn't use that the clustering that much in my model in my pipeline, right? I use it more to kind of some preliminary analysis, and I said, okay, look, these models are telling me that there is some subclustering. I should need to incorporate that in my taxonomy, right?
And I think you explained in your context that your data set is text documents from NASA reports. Is that correct?
Yes.
So
Yes.
after the conclusion of your project, did you implement anything at NASA to help classify documents for sort of in a general case? Or is this still sort of undergoing development?
It's undergoing. I'm still at NASA right now, and yes, I mean, so far we identified this. We created a list of these high trending, high relevance phrases, and we plan to use them for future documents, right? I mean, if they're trending up, we expect them to show in the future. The other thing is like the way we also keep these documents. So if in these documents you don't have a field that says write down the cause of the problem, right? So that's another thing that we're looking at. Like we're looking at how we can improve the record keeping of these documents. So in the future, this type of analysis becomes trivial, right? If you have a field that says, oh, write down the likely cause, then you can just weight your causes in a histogram and say, okay, look, these are the most contributing things and these are the root causes, right? Oh, another thing that I didn't mention was that sometimes the text it doesn't have explicitly reading the cause and effect. So that's another thing we want to do is, these models are great. I mean, they're not AI where, you fill this brain a lot of stuff and then the brain answers you questions about your document set. But it looks more at the structure, at the grammatical structure of the words. So you have, A causes B, right? And if that A causes B is not explicitly written on the text, these models are not going to be able to find it.
Thank you.
Okay, thank you guys so much. Does anyone else have any other questions for the presenter?
Okay, so you have this huge list of common phrases. Have you actually gone back into the reference material to see if there's actually any relevance between the phrases and the sort of final conclusions of the project?
Let me see if I understand the question again. So you're saying if I can find relationships between the phrases?
Sort of see how relevant the actual phrase is to the sort of reference material. So like if, for example, in a discrepancy document, you have the phrase, the plastic coating on the battery prevented corrosion. Like in the Markov chain, you get an association between battery and corrosion, and you make the sort of wrong assumption that the batteries are getting corroded, and that's a common failure. Have you gone back to the reference material to see if there's?
Oh, okay, yes, of course. Yes, that's actually one of the last things I have been doing, is that, okay, once I identified these high trending and high relevance words, I actually went back and looked at all the subgrouping. And what I did was extracting this general phrases thread, like kind of manually, to validate this work that I have been doing. And I would say that the taxonomy was it performed very well on, giving you a subgroup that is very related to each other. But I would say, like, you still need to go manually and extract those phrases, because, for example, here you have almost 700 documents. That every single document has like build redline. It's not true, right? You have like a percentage of appearance there that I actually calculated, but I didn't talk about that much over here. But so you still need to go through them and trying to get the appropriate context from it. Yes.
Okay, thank you.
Okay, if there are no other questions, and the judge is done with their everything, judge, all good? Okay, we're going to move on to the next presenter. Thank you so much to Daniel. Welcome, Nikki from University of Houston. Can you share your screen and introduce yourself and your major of study?
Yes, no problem. Okay. All right, so hi everybody, my name is Nikki Hammond. I'm a fourth year chemical engineering student at the University of Houston, and I did my work under Dr. Lars Grabo, who is a professor with the William A. Brookshire Department of Chemical and Biomolecular Engineering at UH. And my research is in using predictive modeling to improve catalyst performance in low temperature diesel combustion engines. Sorry, one moment. There we go. So to start off, a little bit of background, diesel engines burn fuel more efficiently than typical gas engines. There is just an issue in that they have a lot of emissions, and those are a really big cause of air pollution. So the four main like bad emissions that they have is carbon monoxide, hydrocarbons, nitrogen oxide molecules, and then like particulate matter. And these byproducts are especially harmful because some of them, when they get into the air, they'll further react and create an even more harmful compound. And that can be really damaging to both human health and environmental health. And this is a large area of research being done, is trying to figure out how to make diesel a clean energy, because if we are able to do that, we can reduce the amount of gas we're using and just get more bang for our buck with with using these types of fuels. And a few years ago, Volkswagen claimed that they had actually figured out a way to make this energy clean. There was a huge scandal with it. They claimed that they had a diesel car that was passing all of the emissions tests, even in the stricter areas such as like California. People thought it was an amazing breakthrough. A bunch of them bought the car, and then it turns out that they had a system inside the car that would switch off, and basically they scammed the emissions test, and it was a huge scandal. There's a whole Netflix special on it in the Netflix series Dirty Money. Really interesting and worth watching if you have the time. But that's just really to say that this is an important area of research. It's a lucrative area. People want to see this this cleaner energy. So one potential solution for this is low temperature combustion. So if you look at the figure on the right, that you can see at lower temperatures in this low temperature combustion region, you're actually producing less soot, and you're also producing less of these nitrogen oxides. There's a little bit of a fine range right in here. And so that's where, if you're focusing on that area, it's a lot of it, can be a lot of improvement in the engines. That being said, though, there is a little bit of an issue in this diesel oxidation catalyst in this emission abatement system that we see at those lower temperatures. So in traditional engines, in that traditional diesel oxidation catalyst, they'll use a platinum and palladium catalyst. But on that metal alloy, CO molecules bond a lot more favorably to the active sites than NO. And so what ends up happening is we have an inhibition of absorption of that NO, essentially saying in this diesel oxidation catalyst, those reactions aren't going to, they're not necessarily happening because the CO is poisoning the system. And so the lab that I work with actually did a couple of studies, and they found this alloy A, which is palladium and copper. It doesn't do as well when you just have carbon monoxide, but when you introduce nitrogen oxide, when you introduce nitrogen oxide into the system, you can see that it is outperforming. So here, if you look at this yellow orangish line, the platinum palladium, it decreases its conversion quite significantly when you introduce that nitrogen oxide into the system. And we're really looking at this 100 to 110 temperature range here for conversion rates. But alloy A doesn't do well when it's just carbon monoxide alone. But when you introduce that nitrogen oxide, it's actually doing a lot better. And this is because on palladium copper, when we add in those reductants, we lower the amount of oxygen on the catalyst surface. And so it's able to just react a little bit better. And we're also seeing less competition between CO and NO. So here we go. So my work kind of comes in here, and we were looking at, in that figure, that alloy A, it was just a 50-50 mix, just trying to see like proof of concept. So my work was saying, okay, could we make those results even better? What if we actually are really trying to optimize this catalyst? And so we were saying, what if we run through all of the different potential combinations of copper palladium we can have in the molecule? And we like to call those the different ensembles. So just a little bit of notation moving forward. To do this, to create all of these ensembles, I used this Surface EP package. It's for Python. It was created out of Tulane University, and it essentially creates a 3x3 unit cell. And you can see these unit cells here, and the numbering of the system, really worth noting, it's 0 to 26, not 1 to 27. And it can predict for 7 atomic absorbates and 23 metals, the absorption energies of, those specific atomic absorbates. For our purposes, that's oxygen. And it can test them at 3 different sites, 2 of which are 3/4. It's top, bridge, and hollow, but we noted that there's actually 2 types of hollow sites. There's one where there's an atom behind it and a second where there isn't. This particular program didn't distinguish between those 2 in absorption energies. And you can see that down here at the bottom. You'll notice it's -5.4 for both the yellow and green square. And that's because while this is tested and verified using experimental data and density functional theory calculations, it's still a predictive modeling system. So it's not always going to be perfect, but for our purposes, that was okay. It's still doing what we need it to do. And speaking of absorption energies, you will notice that, again, we were focusing on oxygen, on copper and palladium. Oxygen binds much stronger to copper than it does to palladium, where we want a higher negative value. So this -5.4 at these hollow sites is where we really kind of started to focus on. And so that's where we kind of get to our results, which is after modifying the program in Python a little bit, we can see here a compilation of all of the 200,000 1,000 plus different combinations of these ensembles. So on your x-axis, you will notice we start with 0, which means like we have 0 palladium atoms doped on the surface, and then we're increasing by 1 as we go. So here you have essentially a pure copper surface, and that, or this is pure copper. And then here at the very end where it says 18, that means the top 2 layers are completely replaced on the copper unit cell with palladium. And again, you can see kind of their absorption energies and why we wanted to focus on oxygen on a copper surface, because it does oxygen bind stronger to it. And on this y-axis, we have the absorption energy for oxygen. And really worth noting here is that these are the distributions, these little like bulges, the wider areas, that means that there's a higher distribution of oxygen at those. And you'll notice really interesting in the data is that there's these nodes, and you'll only ever see a maximum of 4 of them, 4 of these distribution sites. And these distribution sites we figured out are correlated with absorption sites. So you'll recall, so we have only 4 essentially types of interactions happening. We have purely copper, 2 copper and 1 palladium, 2 palladium, 1 copper, and 3 palladium. Those are the 4 we'll only ever see. And so when we come back here, hold on. Okay, when we come back here, we can see that we see these 4 different absorption sites. And that's why when you only have 1 palladium molecule on the surface, like you have in this figure here, there's only 2 types of interactions happening, which is why there's only 2 of these nodes. But when you go to somewhere like here, you would see 4 of them. And that's also why when we get to, 17 palladium molecules on a copper surface, you'll only ever have a couple of these 2 palladium, 1 copper interactions, and then the rest will be purely palladium. So that's why there's also only 2 nodes here. Looking at this data, we actually kind of saw something that we thought was really interesting. We decided to dope palladium onto copper because, again, copper has a stronger binding energy to oxygen. And this interaction here, this is the 3 coppers. So when we introduce palladium, as you can see, that oxygen is actually binding stronger to those coppers. And we think it has to do with a neighboring effect. But this was a really unexpected result and can be really telling for kind of future studies. And so moving forward, what we really want to do is we want to focus our calculations on kind of minimizing these really strong oxygen binding areas, because if oxygen is bonded so strongly to the surface, it's not going to react further. And so that means this is kind of the area that we want to focus on. We want this 12 to 14 range, because in this 12 to 14 range, we're maximizing the number of these 2 palladium, 1 copper interactions, which have a weaker binding energy. Weaker binding for oxygen. So that way there's going to be plenty of oxygen on the surface, but it'll also react easily. And, that's going back to this diesel oxidation catalyst reaction. We want it to be reacting in that area. And that kind of concludes all of the research that I did. Further down the line, again, we're going to have to be running a couple more calculations, but now we know where to focus future research in. And really worth noting, density functional theory calculations are really lengthy. They're really time consuming. And so it wouldn't have been possible to go through all of these combinations as quickly as we did had we not used this Surface EP program. And it will hopefully, further down the line, once we are able to test these a little bit more, we can actually potentially put them into an engine and reduce the amount of emissions that we're producing. So sorry, I'm having trouble clicking through my slides. Here are my references, and if there's any questions, I will answer those now.
Okay, thank you so much. Judge Do you have any questions for the presenter?
Yeah, could you briefly explain more about the coding part? So you mentioned the package that you used. Were you entering images of these atom surfaces, or was it like
The
It's sort
package
of-
actually creates those surfaces for you.
create? Okay, so what exactly is your input to the package?
So essentially what you input to the package is, here, I will go back to that slide. So what I'm inputting to the package is I tell it what site I want to look at. So I say, do I want to look at top, bridge, or hollow? Now, the package can run through, it can use 23 different metals. So I have to tell it which metals I want and then where I want the second metal, right? So I say I have a copper surface, I want one palladium atom on it. Now I have to tell it, do I want that one palladium at site 0 or do I want it at 14, 24, and so on and so forth. And the other thing is I tell it, what am I looking at specifically with binding energies? And so my development of the code was really trying to figure out how to run through all of the different combinations. Because again, I did say it was like over 200,000. And so it just can take, you don't want to be hard coding into it, moving that one atom around. Okay, then what if I do two, and so on and so forth. So that's where my input for the code kind of came in. And then also, of course, in the data analysis steps, most the figures that I showed you, those were developed in analyzing the data in Python.
And so when you have your surface of copper and then you're inputting each individual palladium atom, are you accounting for every sort of permutation? So for example, when you have two atoms, they could be at, if I understand, like site 0 and site 1, or site 0 and site 2, site 0 and site 3, and so on and so forth. So you're accounting for every single permutation possible?
Correct. I'm running through all of the different combinations that you could have. So so when I first ran the program, like for one, when you have one palladium, you will only see 181 variations. Or sorry, no, not 181. You see 18 variations because that one can only go into 18 different spots. But then when you go to 2, you see 181, 3 like 245, and then so it's 18 choose like 1 or 18 choose 7, and so on. So it does account for all of the combinations. And one thing worth noting is that, if I put this one palladium at site 6, or if I put this one palladium at site 8 and then I rotate, it's the same molecule again that you're looking at. And so that's why we really wanted to look at the distributions, because you do have kind of repeat structures. But we wanted to say, where would we see the highest distributions across all of them? We wanted to account for those repetitions.
So then is there any type of symmetry where, so you mentioned if you put it at one site and you rotate it, it's sort of the same.
Mhm.
Are you able then to, before you run this code with all these different combinations, can you clean out certain combinations to make everything faster? If you know that there's some sort of rotation or symmetry.
You definitely could. For our data analysis, we didn't want to. We actually wanted to see where we would have those repeats. So we didn't feed out for them, but you could definitely adapt the code too. At one point, I thought I was going to need to. So I even started kind of working on that, but I didn't. In the end result, it wasn't necessary for us.
That sounds good. Thank you.
Yeah, no problem. Are there any other questions?
I apologize if this is quite relevant to what you've been talking about, but do you have an idea for what the relationship between the cylinder volume, the ratio between the cylinder surface area and the cylinder volume is before you get the appreciable combustion effects you're looking for?
So that's going back to like early in the diesel system, correct?
Yes.
I do not, unfortunately. Most of my work is much more focused on kind of just the catalyst. So I wouldn't necessarily be able to talk to you a little bit more, or I can't give great detail about that part of the system. I will say, I was looking for a specific area. Oh yeah, in this figure here, they did actually try to test this in a cylinder on a smaller scale, but when they did it, it didn't quite perform as well in those realistic conditions. And that's really why we were deciding, okay, let's actually try to maximize this alloy.
Okay, thank you.
Yeah, no problem. Okay, if there are no other questions, I guess I will stop sharing my screen.
Okay, thank you so much. So that was the last presentation. So we're all done here. This concludes the computer science division of HOT. Thank you guys for presenting and asking questions, and it was really nice. I understood about half of it because I am a psych major, but it was interesting anyways. But yeah, thank you guys so much. So we're going to take a picture for social media. If you guys are comfortable, you can have your videos on. I'm going to take a picture, and I think that should be good. I think you guys can leave after that. There's a grad school fair after this. You can go hop into that if you'd like. And I recommend that you attend our keynote because it's super cool. But yeah, thank you guys all for being here. So I'm going to take one, just like serious one, and then you can do like school signs or like a funny one. I'll do my like little Sikkim bear thing. So yeah, okay. So 1, 2, 3. Okay, and then the funny or Sikkim bears or whatever the heck. Okay, 1, 2, 3. Okay, thank you so much. Y'all can go ahead and leave and have a nice day.
Thank you, you too.